Very good morning, student. In the previous video, we have seen how a capacitor can be charged. And in order to charge a capacitor, we have to do some work on it. And that work is done by the external source of battery. And that work done is stored in the form of electrostatic potential energy. That electrostatic potential energy can be used by connecting the capacitor in any external circuit. The value of U was half CV square of half Q square by C or half Q into V. Today we will do some more important topic of the same chapter. One of the topic is known as energy density in capacitor. Here the term energy density is basically known as total energy stored in capacitor divided by its volume. That means energy per unit volume. What was the formula of energy stored in the capacitor? That was U equals to half CV square. We know the value of capacitance of a parallel plate capacitor, that is C equals to epsilon naught A upon D. Here I have assumed that capacitor is filled, the space between the capacitor is filled by the air or vacuum. That is why I have didn't take K, right? And what will be the value of V? V is nothing but E into D, that is electrical field into the distance between the plates. Apply this value here, you will get U equals to half. Now in place of C we will write epsilon naught A upon D, and in the place of V we will write E into D. So E square D square, because we have V square. So from here you can see that D will cancel out. This will become half epsilon naught A E into D. So see, this is the one more formula of the electrostatic potential energy stored in the capacitor in terms of electrical field, right? Now you can see that the volume can be written as V equals to cross section area into the distance between the plates. Here A into D is nothing but it is V, right? Here V is not potential, it is volume. So U can be written as half epsilon naught E into AD, and this AD is nothing but volume V. So U equals to half epsilon naught E into V. So U divided by V, U divided by V will be half epsilon naught E, and this is nothing but the energy density of the capacitor. This U can be written as small u half epsilon naught into, oh that's a E square, sorry I have written E here, that is E square basically. So this is the formula for energy density of a charged capacitor. The next topic is force between the charged plate of capacitor. We know that due to induction, the charge on both the plates are of different nature. So that means they must have some attractive force between them. What is the magnitude of this force? Let's calculate that. Let us assume initially both the plates of capacitor, which is one is positively charged and the other is negatively charged, they are very near to each other, right? They are not connected, but the distance between them is infinitely small, right? So there must be some attractive force between them. Now in order to separate the plates, we have to apply an external force so that it can overcome the attractive force between the plates. So in order to place the plate at distance d, we have to do some work on it, right? So let's say after applying some force, these plates are separated by distance d, right? Now, because we have applied force and we covered some distance d, that means we have done some work on it. What will be the work? The work will be force into distance, simple. Now, this work will be stored in the form of potential energy. That means W will equals to U, right? So U will be F into D. We have already calculated the value of U, so U can be written as half Q into V, right? And also V is nothing but E into D, so U will become half Q E into D. Let's say this is equation number 3. Now equation number 2 and equation number 3 can be compared because on the left hand side we have U. So F into D will be half Q E D. So D has been cancelled. We'll get the value of F is half Q into E. So this is the amount of force which acts between the plates of the capacitor. What can be E written here? We know that E is nothing but sigma upon epsilon naught, right? And sigma is nothing but Q by A epsilon naught. So we can put the value of E in this formula. We get half Q square upon A epsilon naught, right? So this is the formula for force acting between the plates of capacitor. Next topic is dielectrics. Dielectrics basically are insulators. That means the electrons in these materials are tightly bound to the nucleus. They are not free to move. That means the dielectric doesn't have any free electrons to move inside the volume of the conductor, and that's why they don't carry current. There are so many examples of dielectric. You know, basically dielectric are nothing but insulators. Like we have mica, we can have wax, air, vacuum. They all are dielectric materials. There is one more thing we know that known as dielectric constant, right? So before we go to the dielectric constant, let's see what is the definition of dielectrics. So a dielectric is an insulating material whose electrons are tightly bound to the nucleus, right? That means they don't have free electrons, right? They don't have free electrons and they don't conduct electric current. The conductivity of dielectric is very low. And for an ideal dielectric, it is 0. So obviously, if you take any dielectric which is idle, that means doesn't conduct any form of electric current, right? So conductivity will be 0. So see, basically, if you want to describe the dielectric, you have to describe the insulators, and you are studying insulator from class 7th. Dielectric constant. You know that if in between the plates of the capacitor, our dielectric material is completely filled, so the capacitance of the capacitors increases by k times, and k is nothing but the dielectric constant. So C becomes k times of C naught. What is C naught here? C naught is the capacitance of capacitor when between the plates we have a vacuum or air. And what is C here? C is the capacitance of a capacitor when the plates is filled by some dielectric materials, right? So from here, K can be written as C upon C naught. So how can we define the dielectric constant now? We can say the dielectric constant of any material is the ratio of capacitance of the capacitor when the gap between the plates is filled by some dielectric material to the capacitance of a capacitor when there is vacuum or air between the plates of the capacitor, right? So this is one definition of K. All right. This dielectric constant is also known as specific inductive capacity. Always remember that this name, or it is known as specific inductive capacity. All right. So this is your dielectric constant. Now let's talk about the polar and non-polar dielectrics. See, dielectric materials or their molecules can be divided into two categories. First, polar and non-polar dielectric molecules. Let's talk about the polar molecules first. A polar dielectric molecule is one which have finite electrical dipole moment. If you remember, we have done this quantity in the first chapter where P equals to Q into 2L. So in polar molecules, the positive charge and negative charge, they are separated by a finite distance. So the center of gravity of the positive charge and the negative charge are separated by some finite distance. Let's take the example of one polar dielectric molecules. Let's say HCl. In HCl, electron of hydrogen atom is more near to the chlorine atom, right? And that is why the surroundings of chlorine become negatively charged, whereas the hydrogen become positively charged. See, some students have this misconception that electron is given to the chlorine, right? It is not like that. Electron is is there only. It is just the center of gravity of that electron shifted towards more to the chlorine, right? The distance between the, now the, we can say, molecule of the hydrogen and the electron is more near to the chlorine molecule. So that is why the environment of chlorine become negatively charged, whereas environment of this hydrogen become positively charged. Now you know that what is the dipole? Dipole is the two charges, right, of same magnitude but opposite in nature, are separated by a small distance, right? So you can see that this condition is satisfied here. These two ions, right, are separated by some small distance, and obviously they having the same amount of magnitude as positive and negative charge. So we can find the electrical dipole moment in this case, and that will be directed from chlorine to the hydrogen, this. Because if you remember, the direction of electrical dipole moment is from negative charge to the positive charge, right? So this is the one example of polar dielectric molecules. So basically polar dielectric molecules have intrinsic electrical dipole moment. That means they already have this electrical dipole moment. We don't have to create any dipole moment by giving some action electrical field, right? They already have this dipole moment. They already have some finite value of dipole moments. Let's say one more example, let's say CO, right? In CO again, in CO, the electron from carbon is, we can say, shifted toward the oxygen, and that is why the environment of oxygen become negative and this carbon become positive. I can see that in this case again the electrical dipole is toward this side. So these are some examples of polar dielectric molecules. There are some more example like NH3 and H2O. Let's take the example of H2O. Here you can see the structure of the H2O, in which we have two hydrogen molecules are connected with the one oxygen molecule. Now you can see that we have two dipole moment here. One toward this side, you can see here, I am making one more diagram here. One is toward this side, let's say this will be P1 from negative to positive, and the other on this side, let's say this is P2. So when we find the resultant, the resultant dipole will be this. That means in the case of H2O, the direction of electrical dipole moment is from the oxygen molecule toward the base line of the hydrogen atom. So these are some examples of polar dielectric molecules. What is the conclusion? In polar dielectric molecules, they have finite electrical dipole moment, right? They already have an intrinsic dielectric moment, right? So what will be the case in the non-polar dielectric molecules? Obviously they don't have any finite dipole moments. Let's talk about it. In the polar molecules, in the polar dielectric molecules, the center of gravity of positive and negative charge is separated by a distance, and that is why they have finite electrical dipole moment. But in the case of non-polar dielectric, the center of gravity of negative charge and positive charge coincides. That means there is no distance, there is no finite distance between the negative and positive charge. So that is why they don't have any finite electrical dipole moment. For example, take the example of, let's say, CO2. Okay, in CO2, two negative oxygen molecule are separated by distance. Where will be the center of gravity of these molecules? It will be here, right? Now, here the carbon atom resides. So you can see that the center of gravity of the positive charge and the negative charge reside. They overlap each other, and that is why there will be no finite electrical dipole moment. There are some more examples, like we can say N2, H2, right? CH4, right? There are so many examples of the non-polar dielectric materials. So today we have completed very important topic, that is dielectric. Thank you so much.